All right, so we were talking about queues last time. That's a nice French word. The next one that we want to talk about is decks. So queue, remember, is something that is FIFO, first in, first out. You push, and it goes to the end, like you're waiting in line. It's a British word for line is queue, right? We analyze things. What are the operations on a queue? You push to the end. You pop from the front, though. It's like the people who are waiting the longest, who were there the longest, they get to be served first. And then you can get the front of your queue, because like the person at the front of the line is the one you want to deal with right now. That's the metaphor. And you can check if it's empty. Sometimes there's size. The queue header file from the standard template library that C++ has given to us. They give us a few extra things, and those are non-standard. So that's beautiful. So we learned about all that. Let's go further. Let's talk about the idea of a deck, which is it's short for something. It's we'll get that on the next slide, but you pronounce it deck. It's like the word queue almost. It's like a cousin, so that's why you pronounce it with a French kind of pronunciation. So it's standing for double-ended queue. So that's kind of what they did. That's they took those letters and they shoved them to the end of the start of that, and that is, or to the start of that. And yeah, what you can do to a deck is essentially stack stuff and queue stuff at the same time. That's all a deck is. It's a stack plus a deck, more or less. You can access the front or the end, but nowhere in the middle. That's all you get. So a deck lets you have these operations. Give me the thing at the front. Give me the thing at the back. Push to the front. Push to the back. Pop from the front. Pop from the back. And also see if the thing's empty. So that's essentially a stack plus a queue together. Does that make sense to us? It's more or less that. You can imagine it's very easy to implement this with a linked list. It's just you have no option of getting anywhere in the middle. That's what you've limited yourself to. Okay? So, yeah, let me draw it. I'll draw it like a queue again, but it's a deck now. So empty deck, got nothing. There's a concept of a front and a back. You can, again, represent it with a list. We'll get into that in a second. But you can now push to the front and to the end. So if I push to the front, that's like a stack operation, kind of. I don't know. Now the deck holds one and only one. You can push front again. Push front the number 2. Now it's the deck 2, 1. And you can push to the back as well as the front. So you can say push back the number 3, let's say, and now it goes 2, 1, 3. Right? And then, of course, you could pop on either side. You can say pop front. And that'll get rid of the 2, so now it's just 1, 3. 1, 3. And you can pop back just as easily, so you could have said that as well. So conceptually, there's no new information here. And now it's just 1 because we popped the end. So yeah, you better believe that you can use a linked list to implement all this stuff. So like, what would that look like? The empty deck would again be the empty list. Nothing there at all, null pointers. The deck with just 1 in it would be 1. The node just 1. Then 2, 1. Like you push to the front of your list. You call that operation on a linked list deep down. Now this would be the 2, 1 list. You just do all those list operations. That's a very easy way to implement this. 2, 1. This would turn into that list, right? 2, 1, 3. Yeah, and this would be 1, 3. So it would look like this. 1, 3. I think you get the idea now. It's back down to 1 just for consistency's sake. You see it. Are there any questions about what it would mean to be a deck? Like you've limited yourself again to accessing only certain pieces of the underlying representation. If we're going to use a linked list, you know that you can go to the middle, you can go to the second node if you want to, but we're going to not give that control to the user of our deck ADT. Okay, that is the difference. So sometimes we have some what's the word? Sometimes we have an assignment or a task that only involves these operations. A deck is the right one to reach for because you can't accidentally do something bad by going to the middle, right? You want to limit yourself because we don't trust ourselves. That's how it works in computer science. Okay, so yeah, it can be implemented with a list very, very easily, and I might as well show that to you. How do I want to say this? Good enough. So, okay, let's talk about it. So Here is how you can make a deck. It can be, of course, a templated class because the kind of things that you put in your deck could be anything. You're just like going there and getting the values back. So it's essentially you're just wrapping around a list. Like you have some underlying list. You can use the standard template libraries list, sure. Give it a list of T's to store your deck of T's. Call it L. And yeah, the only thing you're limiting is middle access. You can go to the front and the end, and you know all of these operations exist on lists. Right? You just call like this implementation for front would be like return L dot front. This one would be L dot pushback that X value that you gave me right now. You're just wrapping around it. Okay? Does that make sense? Questions about how you might implement that with a linked list, with one from C++ or one that you've made. So all of those things are as you would expect. And let's see here. What do I want to say? We'll go there in a second. So we can talk about running times. And there's only one that may not be constant depending on what kind of list you use. So let's see here. How do I want to say that? So let's say I start pushing to, like I've got my deck. I start adding things, and it's turned into this. Like it's got 1, 2, 3 in it right now. I push back or front in some way to get this memory looking like this. Like that's my deck. I've got a first and last if this is my my linked list. Looking at these things. Whee. So you can do that. And now we have to talk about all these operations. So you know that it's constant to get to the front and the end because we have pointers to those things when we're implementing a linked list. We go straight there, get their data, constant time. Push front and push back we also know is constant time because we have first and last pointers. We can very easily add something to the front of a linked list or to the end of a linked list. Constant time, no problem. All right. Same with pop front. It's very easy to get the second thing because that's going to be the new first, like, and delete the old one. Like that's a constant time operation no matter what. The only one that's a little iffy is pop back, right? Because we know that pop back is linear. It's harder if we have a singly linked list like the one we're implementing in our labs. So that means you have to go and find the second to last node by iterating through the list. That's a linear time operation. And so pop back could be hard if it's a singly linked list, but you've been, I've told you enough to know about doubly linked lists, right? You've been reading about them perhaps. Doubly linked lists have previous pointers in addition to next pointers, and those will allow you to get constant time pop backing, just as if it were the front of a list reversed, something like that. So again, it's constant. Checking to see if a list is empty is also, of course, constant time because first and last will be set to null. That's how we're representing the fact that a list is empty. So if we use a linked list for these operations, it's like, that's exactly what we wanted, right? You can't do any better than that. Shouldn't have used a vector, shouldn't have done anything different. A linked list is a great idea. Okay? Questions about that? You see it? Like those will be the time complexities because you're just wrapping around the list ideas. Okay? That's what's going on there. And sometimes there's like a size operation. You have options here. You can trade space for time. So let's talk about that. So let's say we wanted to implement the size operation on our deck. If all we get right now, if all of our member variables are first and last, we get a linear time size operation, don't we? Does everybody see that? Like we have no other way to know the size of a list but to iterate through the thing, find the end. Count how many nodes we pass from first to last. Yeah? No other option. Can we make it constant time though? Is there a way to do that, do you think? How could we improve upon that size operation? So I think we can get it down to constant time if we do something. Do you have any ideas?
We could count the size as we're like inserting or taking stuff out.
Good. Did everybody hear that? Does that make sense to us? If we trade some space, we can gain some time. Very nice. And that's the age-old problem in computer science. How much are we willing to trade? So if we make like a size member variable, I guess we can't call it that because we've used that name, but pretend we can do that. You can start it at 0 when you construct your list. When you make your deck, construct a list inside of it. And then every time you push, any of your push operations, just say size plus plus. That won't change their constant running time, will it? Just one extra line, still constant, that's fine. So size became like you pushed the 1, the 2, the 3. Now it's size 3. And then every time you pop front or back, again, you just add a line, size minus minus. It retains the same running time. That's a constant time operation you're adding. It's not going to mess with that. And so you get the same running time for everybody else. You pop it a few times, let's say. You traded some space. It's constant space to add, which is not too bad, for constant time. And I think that's a great trade. Yeah?
Yeah.
That's pretty nice. So you can turn that into that if you'd like. And that is a good example of making those kinds of decisions. So yeah, those are your operations, those are your running times, and that is what it means to be a deck. Any questions about any of that? We see it all. See the vision? So like I said, a deck is kind of in between lists and stacks and queues. It's like some combination of a stack and a queue, kind of, where you know that a stack gives you access to the front of a list, let's say, because we're pushing to the front, popping from the front whenever we use a stack. Queues let us access both ends in different ways, right? Queues give you access to the back to add, right? You can push to the back, but you pop from the front, so it's a little different. And then decks give you both, right? You get both ends, access to both ends of the underlying list, because that's what we're probably going to use to implement it. You could use something else, but it would be kind of silly. And yeah, that's what's going on. The only thing you can't do is get to the middle. So like here's a deck that you've made for yourself. 1, 2, 3. We know that its representation is this. Could be this. Should be this. And the one place you can't get right now is the 2. Does that make sense? That's all you've given that up, right? Unless you pop. So can't immediately get here without popping. So that's all you get. Yeah. Some things that C++'s version of decks give you are slightly different than what I've talked about. So just imagine that we're talking about the textbook's version of the deck ADT right now. Because there is more. There is more, and we'll get to that. So yeah, are we ready to see C++'s version of decks?
Yeah.
We've studied them a little bit. Right, so let's figure this out. So let us check the docs. Let's figure this out together. And we will find that it is all very familiar. So there it is. It's a container. What can we do to a deck? A good one to click on is the constructor. Like it gives you a cute little example of how people might use a deck. Oh, it's just building it from other things. That's kind of useless. All right, other things that you can do. Size. You can go. This one lets you access arbitrary elements. I don't think that's what a deck is, but they let you do that. It's these push back, push front, pop back, pop front stuff. That's what we care about. So maybe, I don't know, push back. I'll give us an example of that. So there it is. It's pushing a bunch of things to the back of a deck. It looks just like a list. It looks just like a vector, honestly. So it's got a size. You have the size operation on decks. All those things exist. And I think that's most of what I wanted to say. Also notice that there is an iterator. There's C++'s decks give you the ability to go through, right? To go through a wonderful deck like this, so from beginning to end, which is not usually what you're allowed to do. So like that's a thing. So let's see, what's a good example of like why you might want to use a deck to represent something? Or do I want to go and give you an example first of just like this stuff? Yeah, let's just do a simple example of a deck in code just to type something today. I'll call it dex.cpp. And we'll make not a deck of integers. We've talked about that too much. Let's make a deck of strings. Why not? So let's see here. I want to make a deck. It's going to hold strings, and I'll call it D, and I'll just put some stuff in it. So D dot push back. I can push to the back or the front. I'll say hello. We'll push, I don't know, we'll push front this time. Hi. We'll push back world. And you better believe that deck now holds what? Hi, hello world, I think. And you can go to places of that deck. You can go to the front or the back. To get those values, you can change them. These give you back a reference to the things there. So you could set them equal to new things if you wanted to. But we'll just get the things out. Use it as a getter, d.front, d.back. So it'll say, I guess it'll say hi world now, won't it? Cool. Does that make sense so far? Just like a list. And you can go through it. For a weird reason, they give you access to an iterator. You can go to indices. I don't like that, but they let you do it. For, let's say, let's go through this deck using the long drawn-out way of using an iterator. So if I say it equals d.begin, like what in the world is the type of this iterator it? It's going to be, well, of course you can say auto, but if you spell it out, it's going to give you back a iterator into a deck of strings, right? Deck of string, that's the type of the thing. : iterator. It's the type that lives within the type. That's where it starts. Keep going as long as it's not equal to d.end, it++. There, it's off, and it looks like a pointer when you use it. So cout star it and some spaces, and we'll finish it off with a new line to make it pretty. And so that'll print everybody in the deck on a line. Hi, hello world. That was the order. Okay. So technically they don't, I don't actually think they use a linked list when they use decks. What are they doing? Accessed by their position. It's implemented like a vector, surprisingly. There's a way to implement a deck with a vector in a way that pop back and push front, push back, pop back, pop front are still constant. It's a little complicated. It kind of has to like wrap around. You can look that up. All right. There's a way to do that, but a linked list is also a very good idea, and it's one that we can understand. So yeah, that is C++ decks. Questions about that? Useful. Get access to the front or to the end. And there's an iterator. My silliest example that I could think of, I don't know if this is true anymore. I haven't been to Disneyland in a while, but you guys know Disneyland's fast passes, right? I think they're not like this anymore. It's like a pay-to-win thing now, isn't it? But it used to be, right? When you go to Disneyland, you go to the little machine and you can have one fast pass. You can go get one, right? And it was free. But I don't think it's like that anymore, sadly. But back in the day, pretend it's like that now. What was happening was there was, like, you go to a line, like at Disneyland, you're going to go ride a ride. You go and push back yourself, right? Every line is a deck, more or less. You can push back if you don't have a fast pass right now, or you've used your one that you get for the day up. So that's you, maybe, in green. You're pushing back. But those horrible people that got there before you and got a fast pass for that time, they get to push to the front of the line, right? So there's some differing priorities there. And that's kind of a good example of what a fast pass or what a deck could do, right? It could represent this kind of idea of like, you've got a line where normally people are pushing back, like you're dealing with customers in that order, but like if a VIP comes in or something, you want to give them immediate assistance, and like you give them an access code to call push front rather than push back on the deck that is like your customer service deck on your website. Something like that. Does that make sense? So that could be one reason you want to use it. And I think that's all that I wanted to say about that. Are we happy enough with decks? It's very, I mean, it's not anything new, I would say. It's just a simpler list in a sense. So yeah, I would like to, if we're okay, switch to a completely different topic. Are we ready for that? All right. So do shout out if you like, but I'd like to teach you what's called a hash table. So I've said all these words before, but now I'm going to go in depth. So there is plenty more to this. We'll get there in a future set of slides, but I would like to just at least introduce the idea to you. So a hash table is a place where you can store random things. Like you can look up stuff of an arbitrary type and get a value back, which is all very vague. But you can think of like what it's trying to do is it's trying to take an array and figure out where, like, if I were to place a string, like how can I use a string to index into an array? How can I use a vector to index into an array? Something like that. And so like you're trying to take like a string and compute a number from it in a weird way. We'll get into that. So the word hash and hash tables is kind of like hash browns, where like you're actually chopping something up into little tiny pieces. So think of it that way. So that's the kind of definition we're using here. Chop into little pieces. All right, corned beef hash, something like that. So we're doing that to arbitrary data to get us numbers out of the deal. It's very weird. All right. So this is going to answer this interesting question that we didn't really think could be better, but it can. We have seen that if we want to search for something, our best case scenario is to use binary search, right? We make something and we sort it. We make sure it's sorted somehow, or we get it sorted immediately, and we get logarithmic time out of that deal because we can always cut our search space in half. So like this is our ordered thing. 1, 2, 5, 7, 11. Like let's say we're searching for, I don't know, something. We're immediately going to check the middle. Like immediately our search space is the whole thing. But as we look somewhere, like as we look into stuff, we can start cutting off half of the search space each time. Half. Go that way. Zoom in even further until you get to the final answer or empty search space and you're done. You can only cut it in half log of n times, where n is the size of your container, and that gives you binary search. So it's nice and fast. The question of this set of slides is, can we beat that on average? And the answer is yes. Very surprising. All right. So here is a question to motivate that, and I think you can find the answer. So I'm asking you. All right. So let's pretend that we only need, like, our job for hash tables, we're trying to insert values and search to see, did I insert that thing already or not? Does that make sense? So I'll show you that in a second. But let's pretend we only need to insert and search for numbers, 0 through 99. So like this is what you want. You have your black box. Think about what data structure you might use. I'll have you think about it together. So you have a black box and you're like, hey, I want to put 42 inside of this black box. Say that I put it there. I've inserted it. Put it inside there. Please put the number 33 also as well inside of my black box. And remember that. So it's keeping track of the things you've inserted. Does that make sense? And then you can come and ask it later, hey, is 42 inside of this black box thing that's trying to hold on to some values between 0 and 99? Question mark, and it will tell you yes, because you did put that there. And then if you come and you ask, like, hey, is 32 inside? It should be able to tell you absolutely not. You did not do that. You put 33 in, not 32. So that's not there. So that's the kind of game that you want to be able to play. Inserting things and checking if something was inserted. Does that make sense? That's the setup. And let's pretend we only care about inserting and checking numbers 0 through 99. So my question to you is, what data structure would you use to keep track of this in the most efficient way in terms of space and time? All right, so please do attendance if you have not. I will stop that after this question. And try to go to the Written Ice page. I think that would be a perfect place to post your answer. So get into the little peer instruction group, say hello, and elect a leader to post what data structure you guys think is the best one that could stand in for this black box and give us this inserting and searching ability in the easiest, most efficient way. Okay? Please give that a try. And we will come back in a few minutes. Only those numbers. Don't imagine you need to support any other numbers. As long as you have to do you can do whatever you want, as long as you can play that game. What time is this?
If you have to like search through the internet. It's like my thought is like if the number 0 corresponds to the index 0, right? And the following across the search is like I'll go to index 0 and see if it's 0.
All right, here's some time. It'll take another minute or so to decide on something. It's okay. Question?
Or like if you're searching out
Oh, just have to she's logging on.
okay, you know, so like you could have
All I need is reset. It's not going to go.
Yes.
Yeah.
right?
Tell me your last name.
And you list it and you could put like true if the numbers in there.
Okay, so
And you would just have to check the and then add that. So constant.
And you remember to use lowercase for your username?
yes.
Good. All right, friends, this is about to be my timer going off. I'm gonna stop it before it gets too loud. There it goes. Cool. So let's see what we're thinking. I'm excited. I guess you can cheat and look at what your peers have written before you type something. I want to know what we got. Nice, nice, nice. Somebody says binary tree. Nice. Somebody's reading ahead. I like that. Let's see here. Well, yes, hash table is the answer, but the underlying representation of the hash table. I think the most useful answer, the one I'm looking for, is like an array or a vector of not necessarily ints, but I want 100 spaces in there. Exactly 100 spaces, because that gives me indices 0 to 99. Does that make sense? And I can go there immediately because I can access in constant time any index of any array vector. I'll remember to do attendance, by the way. I think someone was having trouble logging in, so I'll leave that up for just a little bit longer. Think about it. What we could do is the following. We could make a vector not necessarily of ints, or an array not necessarily of ints. We could make a vector of booleans, an array of booleans, because that's all we needed. Like, was it there or was it not there? We don't need that much. But, I mean, you could have done it this way, right? You could have been like, every time you push, you add a new value, so like put 42 inside. You could have just done in a naive way, like an easy way to implement this would just be, give me a vector, start it empty, 42, push back every time you put something in there, 33, push back. That is unfortunate because now you're forced to do linear search because it's not the case that the user is going to type the numbers in sorted order, right? So that's a problem. Also, they could do duplicates, like they could add 42 again, and then now you're wasting space. Like you'd have to maybe check. Now the insertion becomes linear time. Check and see if it was there already. That's a problem. So we don't like that. It would be nicer if there's a way to like keep it sorted, like 33, then 42, like after you insert everything. There is a way to do that. I think one of us said it in the priority queue thing. That was awesome. But again, that's hard, and that also it gives you logarithmic time because that would be binary search all over again. There's a faster way. We're just doing 0 to 99. We could use a vector or an array. Just give it initially 100 indices, and let's set them all to false because nothing's in there. Once they're true, like we'll set it to be true when we insert something. We'll call it a lookup table because we're looking up. Like, was 0 in there? Was it not in there? Was 1 in there? Was it not in there? That's our lookup table. We're looking up to see if stuff is in there. We can easily go to those indices. But initially, at the start of time, what do we got? A bunch of indices all set to false. Dun, 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 dun. So that's quite nice. Up to indices 98, 99. Lovely. And then we can insert and search in constant time, can't we? Because like, you can be like, if you want to insert 42, you just go to like, hey, lookup table. I can't spell well. Lookup table at 42. Set that to true. Yeah, constant time. Beautiful. Check and see if it's in there. It's just like, hey, lookup table. Why do I want to put that right there always? Oh no. Have I ruined my... There you go. Lookup table at 42 again. Hey, was that true? Something like that. Of course, you can get rid of that equals true. That's redundant. But again, that would be your condition. Like, and they're both constant, right? That's constant. That's constant. Like, you cannot do better than that. Any questions about that? That's not horrible. Does that make sense? Like, how easy that would be? Like, if we had just the numbers 0 to 99, so not too many, we could use just a 100-sized vector or array of Boolean values. There's a way to get the compiler to use 1 bit instead of 1 byte per value. Like, it's really cool. There's a specialized vector of bools, actually. Let me show that to you because it's kind of interesting to think about. This is why you have this. Like, there's a generic vector of any t's, but they've made a special vector of bools efficiently. They've specialized that particular thing for bools so that they save space that way. They're using bits instead of bytes when they can. So that's something you can think about. But besides, it's beyond the scope of this class. So yeah, that's pretty nice. That's kind of our pie in the sky dream. If only I can make a lookup table that works for anything that kind of looks like that. That's where we're going with hash tables. It's like, if only all the values that I ever wanted to insert were small numbers that could be an index into my lookup table, and there were no gaps at all. Like, I'm always gonna want those numbers 0 through 99. I'm never gonna want to skip over anything. That would be my dream, right? Because then we could solve it with that and call it a day. Go home. Okay? That is lovely. Let us complicate the problem now. All right? So those lookup tables are awesome when, like, you want to, first of all, you're inserting and you're checking to see if something is inserted. You don't care anymore. You've now lost, if we do it this way, right, we've lost insertion order. We have no clue. We just know, like, 42 is in there. We don't know when 42 got in there. Does that make sense? That's important to think about, all right? There's no concept of time anymore. I guess you could make a fancier lookup table that, like, every time you add, it just, like, increments a counter or something. Like, you could keep track of time in that way, but it would get complicated and it would turn into linear time, checking for the second thing. Like, you don't want to care about that. It's just like, was it there or was it not there? That's the problem at hand, all right? You just care about, does it exist in our table or not? We don't care about the thing that came before, the next smallest value. Like, there are other data structures for that we'll get into, all right? So that's what we want. And so our goal is to make lookup tables and also save space as we do it, okay? That's where we're going. So an interesting example that kind of highlights this problem, like a problem with this approach, is like to make a phone book. Like, that's a nice idea, right? We all remember what phone books are, right? It's like a book that was delivered to your home that has everybody's name in alphabetical order, so you could binary search and find somebody's phone number next to their name, okay? Let's make a reverse phone book where you have a number and it looks up a name. That'll be nice, because then we can use the number as an index. That's where I'm going with that, right? So we can make a lookup table that just, I don't know, stores, we don't care about the area code, it stores how many, we need 10 million spaces, right, for all those possible numbers, and we'll just make a vector of strings, because the thing at the other end, right, the thing at all our indices are the strings of the people's names that are in the phone book, yes? So that's kind of nice. Let's do that. We'll call it a lookup table. Dun, dun, dun. Lookup table. That's a good beep. So I'm going to use vectors of strings. That's going to be my phone book. Vector of string called phone book with a capital P, why not? And it's going to hold 10 million indices. I think that's right. And that's the vector constructor. You just tell it to build that many things, default construct a string, which means it's empty strings at each index right now. Okay, that's what's going on. And I would like to add, if you do it this way, right? Like if you want to put something in, it's a dot at. If you want to look up, it's also a dot at and like get the value out. So insertion, if we do this, right? Insertion becomes constant time. Cool. Also removal, like if you want to get rid of something, you set it back to empty string. Removal also becomes constant time. That's supposed to be an M. That looks weird. Let me fix it. Beep. We got that. And then to get the value out, like go to the index again. Just look at the thing. That's retrieval. Retrieve. Again, constant time. You can't do better than that, right? That's beating binary search, isn't it? That's kind of cool. So there's a reason we're studying this. So yeah, inserts constant, like phone book at, I don't know, this is my phone number. Boop, equals, that's my name. All right, maybe I give my cat a phone number. He gets the next one. Like that's insertion, right? Insert is constant time. Retrieve is also constant time. Go and look at something, like get the value out, please. Who's at phone book, the phone number 8675309, right? Who's there? Who's at that one? So that's what you can do. If you only want to store 2 numbers in your phone book, we have wasted a lot of space, though. Yes, you see the problem? That's a huge problem. There's a lot of wasted memory. But oh man, did we make a, I don't know, if you have the memory, we made a great trade, didn't we? We traded space, a lot of space, for constant time, though. That's lovely. Okay, that's what we just did. I pressed a button. So there they all are. You see that it lagged for a second because it was making all that memory. That's hilarious. Okay, so that's a little disgusting, but it's working. Any questions so far? All right. So yeah, constant time. That's wonderful. The goal of like lookup tables, what a lookup table can do is you give it a number, right? It takes indices, something that is a number, whole numbers only, and you can get back any kind of value because at every index you can place anything. You can make a vector of strings, a vector of bools, a vector of doubles. You can retrieve any kind of value. You just make a vector of that kind of thing. Does that make sense? But the things that you put in, the inserted things, are numbers. Like you go and you look up a number because that's got to be an index. Yeah, that's the downside right now. But yeah, time and space complexity is constant. It just takes a lot of space. So like, because just assume going to an index of a vector takes constant time, and that is true. That is what happens because you're just going to an index of the underlying array on the heap, aren't we? And that is just calculating an address and dereferencing that address. So cool. Insertion, constant time, just go to the index where you're looking at, set the value there. That's exactly this. Constant time. Beautiful. Removal, also constant time. Just go to that index and set the value there to, like, I guess for this one, it's empty string would be it's not there. You could also have some sort of like non-existent marker value. Like there's something that you could do there that you could play around with. But removal is, again, constant time. Just go to that place, because it's a number, it's an index. Go to that index and just say, no, not there. You start them all off like that. And then retrieval is again constant. It's just like go to the index because it's a number, right? You're looking up a number and get the value at that index because that's the thing you've stored associated with that number. You're associating a value with another value, a number with a string in our case. Yes? So yeah. Does that make enough sense so far? Like that's what we've talked about. But the space complexity is disgusting. Technically, it's constant space but it's just a very large constant, right? So space complexity of our lookup table for a phone book, just you can imagine it gets disgusting if you want to include area codes, right? Or like non-US and Canada phone numbers get even worse. But yeah, phone numbers would take a 10 million size table if we're just dealing with one area code. And we don't even have one area code in this place anymore, do we? Like we added a new one in addition to 559. Crazy. So, okay, technically constant space, but that's disgusting if we just want to, like, it's our phone. We just want our own personal phone book with our friends' numbers, our parents' numbers, our siblings' numbers. Okay, so that is the next step. I'm trying to give you a logical progression to this thing called a hash table. So it's unfortunate, this example, right? I only have two things. I would like to have a phone book vector of strings that is proportional to to the amount of things I want to place in there. Don't just make it 10 million. That's the goal right now. All right. It's like an issue arises if we want to insert like a wide range of things. Like we've got a wide range of possible values like phone numbers, and we've got a small amount of things we'd like to insert though out of that wide range. So, for example, in addition to phone numbers, a good example would be like our student ID numbers. Like your student ID numbers are like vastly different, more or less, from one another, and they're also very large. So there's only ever going to be in this class 71 people, but they don't do that, right? 71 people are allowed in this room at once, but they're never going to cap the class more than 50 because there's not that many computers. So there'll only ever be 50 students in this room, and at a maximum. If I want to store your student ID numbers, if Canvas wants to store your student ID numbers, do I need to make then a vector with like tens of millions of things, like however big a student ID number is, because I've forgotten how large it is? That's too big, right? If I just want to store 50 things, that's a lot, right? If you've got, I don't know, just imagine it looks like this. It's so wide, but like I want to store that ID number, that index, that ID number, that index. Like say that they're there, put a name associated with them or something. Like maybe that's what I want to do. Like this is my student ID number. Some of them start with zeros. I want to store names with student ID numbers rather than phone numbers. Like that would be disgusting again to play this game. If you make that size of a vector, only using 50 indices, that's too bad. All right. Instead, our goal, that's a waste, right? What we would like to do is find a way to take this number, this number, and still use it as an index, but of a much smaller table that is proportionate to the size of, or to the amount of things that I'm ever going to be inserting in it. All right, that's the goal. So maybe rather than a 10 million size table or whatever, let's make a 100 size table. It's proportional to the number of things I'm inserting. If I've got 50 things to insert, it could be double, that's fine. And let's say that we've got a way, let me redraw the arrow. Let's say that we've got a way to shrink down this number and make it be an index of this array. Like somehow we found out that it'll go right there. And we'll place our value, place lot in there. There's a way to shrink down this giant number to be an index of a much more manageable sized table. Does that make sense? What I'd like right now? If I could do that, if I could shrink down this large number to like 98 or something, 97, that index, then, and if I could do that with everybody's student ID, like I can place somebody, like one of my method might take somebody's there, somebody else is there. There's still going to be some gaps, but not as many, and I'm not wasting a lot of space anymore. That's what I would like. I would like a way to shrink down large numbers, or anything, honestly, to smaller things that could be an index of a manageably sized table. All right, and that process is called hashing. We're chopping up that big thing, making it small. Okay, does that idea Like, I haven't told you how, but does that idea make enough sense to us? Like, that's what I would like. If I could have that, I could have the best of all the worlds. I could still do this process, but I could make a size 100 phone book. Boop. And it's so much better, yeah? Save so much space, and I still get the constant time out of the deal. Does that make sense? That's what I would like. That's what I would like. Is there a way? That sounds like a dream, right? Is there a way to make that happen? There kind of is. It's math at the end of the day. So the idea of hashing is, again, shrinking something down, like taking something, converting it to a number that could be then used as an index, okay? So here's the goal. We want to shrink down a large input space to a small range of things, all right? And we would really like it so that every time, like, we're doing the shrinking process, all the different values we could ever want to shrink, they're being shrunk to different values, right? Because we don't want to take a bunch of things to the same index. That would be bad. So, yeah, we'd like that to happen. We'd like each index of our lookup table to be equally likely to be chosen by our shrinking process. That's our goal. That's our mathematical goal. So let's say I've got a bunch of things that I want to shrink down, like phone numbers. There's a phone number. And we can get technical, but this is just a silly, simple example. Like, all right, here are some phone numbers. I'm making up some random numbers right now. That one, 555, 5555. There's my phone numbers, and I've got n of them, let's say. N things. My goal is these are my friends, and I like to place them into a phone book. Right? I'd like to save their names associated with their numbers, and my goal is to put them into a size vector that is proportional to n. Okay? Put them into a O of n sized vector, proportional to n itself, not size 10 million. There's a way. All right, that is my goal. So, I don't know. Maybe our vector could have 10 indices. That's proportional. That's better than 10 million. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's better. Okay, if I could do that, that'd be great. And here's the way. I could make what's called a hash function. It's a mathematical function that'll take this idea, this big thing, and shrink it down to an index. And it'd be great if it would be different each time for my problem at hand. Sometimes you can't get that. Sometimes you have some overlap. You don't have to deal with it. But there is a way to calculate an index of this particular vector that's different for all of these numbers. Does anybody see an option? What kind of math could I do with these? You see the last digits are all different? That'll work. So that's my hash function. There it is. I'll call it h, and h will send this big thing to 9. It'll send this big thing to 7, this big thing to 6, this thing to 5, this thing to 3. Do you see how it won't work for everything, obviously? There's ways to solve the problem if there's overlaps. But do you see that there's a way? There's a way to make it smaller and place it in a proportionally sized vector to the number of things I want to insert. We can have our cake and eat it too with hashing. This is beautiful. All right, so that's what you can do. And so I don't know, maybe the one that goes at 9, that's my phone number. Like, you save my name there, L for Lawton. 7 is some other person's name. 7, person A. 6 is person B. Like, you can go to those indices now that you look it up. It'll take you to that index, right? Same game. 5, person C, which looks like an L. There. And then 3 is person D. Cool. You save their names or something. Nice. And so, yeah, that's what's happening. We're able to shrink what's going on there. The technical terms are a lookup table is always mapping keys to values. It's like a key is something you're using to unlock the value. You're going and, like, the numbers, the phone numbers are keys in this case. Like, we're using a phone number. That's our key of our hash table to look up somebody's name. A string is the kind of values that we're getting at, the names of people. All right, so it's always there's always two types involved: the type of your keys, the type of your values. One's being used to look up the other. And yeah, through this idea of hashing, you can have some operation, some algorithm that takes a big thing, makes a small thing, or at least a smaller thing, or at least a whole number that you could then use as an index. All right, and yeah, that's the goal. Through this idea of hashing, we can shrink our input space. Let's play the phone book game and see what happens. All right, so taking this program, let's do it with hashing instead to save space. We'll get the same time out of the deal, though. Look up table with hashing. So goodness, what do I need here? I've got a phone book, and I'm going to make it not of size 10 million, but of size 10. Boop, just like that. And I can't just go to indices anymore. We got to play a different game. Let's make an insert function and a lookup function. All right. So I'll say that, hey, boop, I would like to insert into my phone book. It's called phone book. I'll just make a function. At that number, that name. All right. That's how I'll call my function. And yeah, that'll work. Do the same for the other one. Insert into my phone book at that number, Alonso. Okay, that's what I like. And then I can do the same with like a lookup. I can say, okay, I'd like to look up in my phone book. Look up in my phone book this value, and then I want to print out what I see there. Okay. See out the result of looking up in the phone book this value. Same for the other. Does that make sense? That's what I like to have happen. So yeah, still going to be constant if you think about it. Let's figure this out together. So insert and lookup. So it's going to be void insert, right? We're inserting into some vector of strings. String reference, right? Taking it by reference so I can mess with it, call it v here. We've got an integer key, that's the thing that we're using to do the insertion at that place, and a string value, string val that we're trying to put in there, all right? So the goal of insertion is to shrink the key down to an index of our v, in this case, okay? Shrink the key down, using some math or something, down to an index that's part of v. And there are a few different schools of thought. There's one idea that hashing is just a way to take some type of things and make some whole number out of the deal, and then you can do the shrinking later. I'll show you how. Some people also think that hashing is the idea of like doing all of that at once, like taking a type to something and then making it shrunk at the same time. But that will become apparent later. Okay, so a very easy way to take this and compute a valid index that's always somewhere in my vector. Like, first of all, how do I get this last digit? What's the operation in C++ would do that for me? Do you remember? It's going to be the percent sign, the modulus operation, yes? Yeah, is that coming back to us? You better go review that because that's going to be very important. So it's modulo. The modulo operation. The percent sign is a great way to always shrink a whole number down to a valid index, to do the shrinking. I just happen to have a size 10 thing. I didn't have to have a size 10 phone book. So modulus with 10 is going to give me the last digit, but it didn't have to be like that. All right. So a nice, easy way to take an integer and calculate an index that's always somewhere in my vector is say, like, here's the index that you should go to, key. Modulus with v.size. Because isn't this great? Like, this will always give me a valid index. Because if I say mod size, like if size is 10, if you get a remainder after dividing by 10, you're getting 0 through 9. Yes, those are the possible remainders. That's every possible value, every possible index that you could want to go to in your vector. And that works for any kind of size. Isn't that beautiful? That'll always put it somewhere that's there, all right? So if you do mod v.size, always, it's going to give you a number between 0 and v.size minus 1. And what do you know, that's an index. They're all going to be included. Nice. That's lovely. That's as good as you could hope. So that's that's a great way to do the shrinking. Okay. And then you just say there, say v at that index, go there, and put that value in there, please. That's what you do. Does that make sense for insertion? Cool. And then same for lookup. We want to do the same for lookup to get out the string that's in there, right? String. It gives back a string. We're going to call it lookup. It's going to take a vector and a key that we want to look up. And then it's going to give that string back that it sees there. Again, it's going to find the index, right? What's the index where that thing was, that key was? Well, it's the one that we can calculate in the same way. Going to do the same process, right? And then just go there, return the at that index. Give me that value back. So did insertion and lookup make sense to us? We're shrinking down that value to potentially large key to an index, always a valid index, going there and either updating the thing or getting the thing back. Yeah. And the same exact thing is going to happen here. In the blink of an eye, because it didn't waste a ton of space. This is all still constant time. Does that make sense to us still? It's all still constant time. Like doing this modulus, that's just division. Division getting a remainder, that's constant time, this line. Constant time. Insertion and lookup, still constant. Lovely. So constant lookup time and linear space in terms of the number of things you're going to want to insert. It's proportional now, which is better than the giant constant of 10 million. Still better. So I mean, you're kind of forced to have linear space, aren't you? Like you're gonna insert your n things, and they better be in memory somewhere. Like you can't do any better than that. You can't really like compress it in some weird way. Yeah, so that's hashing in a nutshell. Are there any questions about this process? Like you got something large, you want to shrink it down to a valid index. Modulus, if you got an int, is a great way to do that. Cool. So you can imagine there are still problems with this. If you had two numbers that ended with 9, we're ruining something there. We're losing one. There's things that you can do to make this fancier and get around that problem. So we'll be going there soon. Okay. But yeah, maybe think about or read ahead and like see how you could solve that. There are different ways to do it. So we'll continue with hashing later. We'll have a whole set of slides dedicated to those. But that's a good place to stop. I think to stop on hashing at least. So I've got a few more things to say still, of course. But yeah, we'll continue with hashing later. Here is just a cute little question that I came up with. It took a long time to draw this image, but to paint this picture, but I think it's a good idea and it gives us some good practice. So let's say, I think we do have time. I don't think you have to write this. I don't want you to write this down anywhere. This is too complicated. It's not even easy to make, but just like amongst yourselves, you can discuss and then I'll show you how to think about it. But let's say you've got a bunch of data structures that you know how to use now. And let's say that you've got this. You've got a list of stacks of queues of integers. That's what this would look like, right? You've got a list and you've got a pointer then to the start of it. There's your first node n. It's a list. Inside of every list node is a stack. Inside of every stack element is a queue. And all the elements of a queue are integers. Does that make sense? My question to you then would be, how in the world could you get that 5 out right there? And know that it was a 5 and print it? Let's say you wanted to see out it. Discuss amongst your neighbors, like starting with n, if that's a pointer to that first node, how could you just like write out the sequence of things? You don't have to write the code if you don't want to. Like, how in the world could you get that 5 out? Because you know all the operations. Do you remember all their names? Help each other to remember them. Figure out how to find that 5 and print it. All right? Questions about the question? So take a couple minutes, just like start naming operations and following them on this page with your finger or your eyes, and see if you can all agree on the order of which named operations will get you to that 5. Okay? Please try that. Good practice. We're combining the instructions in this one. And then I'm using the
So like if I wanted to calculate the list, what would I do?
I'll give you another 30 seconds to stare at that and consider things. And I'll show you my thoughts.
I think it's not necessarily.
Yes. Like, would someone, like, are you asking if I can think of a reason to ever want to make this exact data type?
Yeah.
No. But, but I'm sure we could find a way. What could we want here? Yeah, no, it's a little complicated, but it's still a good example. I'm sure there's something somebody could cook up to warrant this, but I think it would take some thought for sure. Yeah. Let's see here. Yeah, so are there any questions that came up as we tried? Any other questions? Or I show you like my way of thinking about it. It's like somebody made this thing, called it L or something. And then you can also think of it like I had a pointer to that node. Like if you want to think about it at the data structure level, like I need to get to like think about it in order. Right? I need to get to this list node first. I need to get to the middle list node, don't I? So that's n next. Will get me there, right? So now I'm here, yeah. And then the data part of that is the stack. So I need to get to that data part and next data. And then what do I want to do once I'm at the stack, right? I got to pop the stack, yeah? I better pop the stack because I can't get anything. I can only get the top thing. The thing on top is not what I want. So I better pop the stack, right? I got to get rid of that. So these arrows are no longer making sense in terms of like C++ codes. Like these are the things you do. Start and go to the next thing, get the data, pop the thing there. And now the thing on top is something I care about. Get the top element of the stack, right? Give me the top. And now that's a queue. And if you want the middle of the queue, you can only pop from the front, right? You only get things out. Look at the front. So the 6 needs to go, right? So we're gonna pop that queue. Now we're at the queue. And now the front is 5. So if we get the front now of that queue that we're at, I see it. Right? These arrows are not correct. Some of those are going to be dots. Some of those are going to be real arrows in C++ land. But I hope you kind of see it. Like that's how you could go there. Does that make sense? Is that what we came up with? Nice. So yeah, I think that's all that I wanted to say about lecture stuff, data structures and things. Are there any questions about anything that we talked about today before I talk about something that's more like lab related, like GDB kind of stuff? GDB adjacent. Ready for that? All right, last topic for the day, if we are ready for it. I want to teach you about a concept called sanitizers. There are some programs that some very nice people have made for us that check for things that are bad. One bad thing that we've talked about a lot, that we've run into a lot in CSCI 40 and CSCI 41 is undefined behavior. It's when you do something weird that doesn't like match the specification of the C++ language. Like you forget to say something, or you forget to give a value to your variable. Like you declare it, but you don't assign to it, and then you try to use it. You get random stuff out. That's an example of undefined behavior. All right. So some people have made some nice programs to go and check for those things, and those are called sanitizers. So it's trying to make your program clean. So yeah, it's another way to debug. So there's more to it than just like Valgrind we've seen. GDB is like super powerful and nice. We've seen that too. But there's other things. A sanitizer is just some program that's going to go hunting for bugs by changing your program around. It's like it's inserting some stuff when it's compiling. The sanitizer is to make your program maybe run a little bit slower because it's making some checks that happen between lines. But like it's adding little mini if statements into your code to make sure like, does the universe still make sense in terms of the program right now? That's what it does for you. It's like making sure to see if you did anything weird wrong, stuff like that. So the most popular ones, the ones that I'm going to teach you, are called ASAN and UBSAN. All right. And what ASAN, the A in SAN stands for sanitizer, but A is short for address, so stuff with memory and pointers, and UB is short for undefined behavior. So I'll show you both of those. I cannot spell. Behavior. Something like that. Cool. So that's where we're going. Let me show you the address sanitizer first. What it will do is it's going to find memory errors in C and C++ programs as they're running. So again, what a sanitizer does is it inserts checks into the compiled code, and when you run that program, it's going to do its little checks, and it will yell at you if any of those checks that it inserts that check for memory safety stuff fail. Okay, so I've made a couple pre-made examples. It took some thought, so let me copy those in. What's the name of the folder? Sanitizer. So it's 4113. Cool, we got this folder now called sanitizers. And here's the first one, ASAN. Let me get rid of the compiled files. There they are, CPP files. So here is a program with a problem. So it's got an array of 42 things, and I'm going to undo some of these so we can see them happen. Let's get rid of all that one, that one, that one. So they're all there right now. They're all going to run. Let's see here. So here's a bunch of problems. There's size 42 array on the heap. It has indices 0 to 41. Here I am going somewhere silly, trying to write a value there, a hexadecimal value for cuteness' sake. You can delete the array on the heap. Shouldn't do that twice. It's a bad thing. And then also, if you forget to delete stuff, that is also a memory leak as well, right? So this is just brand new memory on the heap. That is, I'm forgetting to delete it, and you know that Valgrind will show that to you, but ASAN will also do that. It's part of its job. So cool. It's a competing idea. So the way that you have it insert these checks is you say -G, because you know that gives you GDB stuff, and like it inserts like line numbers into your code, which is super nice. It needs that there too. And then you say -F sanitize equals address. You put that in term as you're compiling, and then it's happy. So that's what we do. And I will compile that in that way, and then you just run it. And it's got those checks going as you run it. So the program's a bit larger than it would have been. It's got some secret checks being inserted after every line, making sure the world still makes sense. And so here it is. It's very pretty. Whee! It runs and it like produces colorful output. I love it. So the first one, it's saying, oops, heap buffer overflow. So here I am on the heap. This array is on the heap. I'm trying to go to a place that is past the end of that. It's heap memory that does not belong to me. All right. Write of size 4. So 4 bytes and integer size of things go in there. How dare you? And it's trying to say like where things happen. It says on line 9 was where the write happened. So that's super helpful. It's kind of like GDB in a sense, but it's running the program at the same time. It's cool. Like it'll produce output as well. So you got that one. And then, yeah, just like how dare you, and it's trying to give you some helpful information. But like the first stuff was the most important stuff. So like it aborts the program when it notices that happening, because undefined behavior will ruin the rest of your program potentially. Okay, so that's why we check for it, and that's wonderful that it's doing that for us. Okay, so that's that one. If I comment that out, it'll find the other things. Try it again with the double free. Cannot delete memory twice. It's like, how dare you? Attempting double free at that address. That was apparently the address of the array on the heap. It's like, you did that. How dare you? On line of your code. Always got to find your own code. There it is, lecture 13. Line 13, there it was. So go there, fix that. That's very helpful. And yeah, just like showing you where things are. Again, it stops the program. Okay? Do you see how that's very useful? Like, these kinds of problems will, like, I guess this would have been a runtime error, but it's really, really helpful. Really, really helpful to make sure you're not doing wrong things. And then the last one, memory leak. It'll find that too. Whee! So it's kind of a competitor to Valgrind, at least for this thing. It's like, oh, detected memory leaks. Here you go. It was the new happened on line 16. Oh, cool. And then it's like, I did not find a delete. So it'll tell you where it got created, but not where it got destroyed, because it's never getting destroyed. Is there a question?
When making a sanitizer like this, is there a way to make it more readable, or is there a reason why they have it so?
This output? Why this output looks like this?
Or does it kind of have to find the sense of it look like that?
Yeah, I mean, it has its own little internal representation of all the things that's gone wrong, but it is, I don't know, it's trying to be as helpful as possible. It's outputting things, like separate things on separate lines. It's just that my terminal is so large right now. So it is pretty kind of as you could make it. So you can go and make a program that goes and finds things for you. But yeah, I guess my question is like, what would you prefer? Like, what would you like it to look like?
I was just wondering, because I guess especially when zoomed in,
Yeah.
hard to parse.
Yeah, so zoom out, it looks much prettier. It's like, it's trying to color code things, giving you the stack of where things happened. I think it is kind of nice, if you zoom out at least. But yeah, you can there are people who write programs that wrap around, like you can take this output and like parse it in a way and make it prettier if you want. There's definitely things that you could do there. And that would be fun to learn about, I think. So yeah, that's a good question. Other questions about this? So it's fine, the leak. This one doesn't abort the program. Just telling you it happened. So that's quite nice. 4 bytes leaked and 1 allocation. So 1 called a new. So yeah, that's that one. And it'll show them all to you. And if you fix that one, then it just runs your program normally. It gives you the normal output that would have been there. And there was nothing for it to yell at you about. So that's quite nice. So that's what you want, in theory. So it's inserting some checks to make things nice. All right, so that's ASAN, doing memory stuff. And then UBSAN is for undefined behavior, which we've talked about in general. Just like the word undefined behavior is, you got code that goes against the C++ language rules. And what undefined behavior means is it's legitimately what you have done is undefined. Like you're using a variable that you've declared but never given an actual value to. If the compiler notices that you did that, it knows that it's undefined. What happens, it can do anything it wants to your code at that point. All right, it can replace code that it finds that contains undefined behavior in any way that it wants. A lot of the time it's just going to delete it, which will mess things up. But technically it's according to the standard, I guess the compiler can empty your bank account every time you have undefined behavior in your program. So you want to check for that. So in the same way, -G fsanitize equals undefined this time. You can have both of them at the same time. fsanitize equals undefined, fsanitize equals address. It's just adding some checks. It's when the program's running, it will find these problems, which is quite nice. It's like checking the memory, checking the values of things. So let's go to that one. UBSAN. Dun, dun, dun. So we're going to compile this one like this. -G fsanitize equals undefined. And let's make sure that, did I accidentally? No, I'm just going to keep them all there. Cool. So here are some problems. Here are some examples of undefined behavior. The compiler is even giving me a warning for one of them, so it notices that off the top of the immediately. But we could have hidden this in like a different way to make it not notice. But let's pretend that we're just gonna ignore that. And so here's 3 stack arrays, just for fun. And this one, I'm going into a weird place, right? I'm going past R2, but potentially into one of these other arrays, like depending on how the memory is arranged. Like there I am going to a weird place of R2. May hit memory that's part of me still, but not a place that's part of R2. Okay, so that's happening. You got an integer. You know that this is the right shift operator on integers that will shift that many bits over. There are only 32 bits to shift over. So I guess 31 would make sense. 32 would zero everything out, right? So, or make it all ones. It's an arithmetic right shift. That's beside the point. There's too many bits. Too many bits, more than 32. So that's unfortunate. There's a nice constant called int max, which is the largest possible integer that you could store. I'm placing the largest possible integer in Z. And if you add 1 to that, it is going to overflow. It's going to make the, let's see what will happen. It's going to make a negative number at that point. That's just the way that integers are arranged in memory and the way that they look. It'll spill over into negative land. Is it going to be the largest negative? Yeah, I think it's going to be the largest negative number. So that'll look funny. And then here I am dereferencing null, which will be a runtime error, but UBSAN will hopefully catch that as well. So here, I compiled in this way. I've got the program that I could run. I got a warning from the compiler even. UBSAN, if I run it, dun dun dun, yay, look at us. Here we go. And then it's got the sigful at the end here. So what we see is, in our output, let me zoom out a little bit. It's like index 58 out of bounds for type int of array size 55. It notices that. And it gives you the line number too. It's like, all right, line 10. Oh, sorry, line 13, excuse me. Line 13, how dare you. Column 10 even. That's where the indexing ended. It was very helpful. Index 58 out of bounds. How dare you try to put something at that place. So that's line 13 problems. How dare you. I was trying to give you other helpful information. So there's that one. And then saying shift 35, too big, line 17. Don't do that. Bad idea. There it goes. And then this last one, this other one, integer sign overflow. It's like, oh, it notices the overflow. It checked that the value like wrapped over. It did not get more positive. It went from positive to negative. Disgusting. This is the largest integer, by the way. Adding to 1 cannot be represented in type int. So that's undefined behavior. It will just wrap over on every computer these days, though. And yeah, the last one, it notices the null pointer dereference. And so if that wasn't clear to you before, like it doesn't say, usually it just says segfault, right? And you don't know, like, was that a bad address? Did I have a bad, like, undefined address? Did I make a pointer variable and never give it something? Like, it's telling you, no, that was null this time. That's useful as well. So on line 25, it gives you the line numbers, tells you when things happened. So consider compiling with this one and this one, like, modify the makefile that I give you for your labs, and check those things as your programs are running, as the tests are running, because that will help you pass them. Yeah. I think that's all that I wanted to say about those. Any questions about either of those? ASAN, UBSAN? They're just inserting some checks that run as your program is running. So it makes your program a little bit slower because of that. But so you don't want to like give that to the final user. You want to use this as your debugging, make it perfect, then ship your software out to the world. But yeah, good ideas. Good ideas, good knowledge. And of course you can combine. So you can actually use the comma. Now that I'm glad I made this slide because I've forgotten that already. You can combine your fsanitize equals address comma undefined, no spaces because it needs it all in one little chunk there. And there are more than just those two sanitizers. There's one that deals with when you get to fancier classes where you implement like parallel things. You could have multiple threads if you know what that means, running at the same time for your program, and then you can have weird stuff as they're trying to fight for data because they all share memory when you have multiple threads, and that's disgusting. So there's problems and checks that you could add there too, and there's more where that came from. So look into that if you're interested. It can only help. And I think that's all that I wanted to say about sanitizers. So that will help you write better code, cleaner code, right? You're sanitizing it. So I think that's all that I wanted to say. Any questions about that or anything else? So I think that's all that I've got for us. It's just the lecture for the week. Yeah, that's all I have. No new assignments. The rest of the time is all yours.